name is Dana Golden. We're going to continue on with an introduction to Numpy. So here we're going to do our imports: import Numpy, import pandas, import matplotlib. Here we're just going to take the dot product between 3 and 4, and then we're going to create this one matrix A, which is 1, 0, 0, 1. So this is really just the identity matrix. And we have the second matrix B, 1, 4, 2, 2. So if we multiply A and B, if we take the dot product, what do you think is going to happen? We get back 4, 1, 2, 2. Remember, A is the identity matrix, so if we multiply them together, nothing changes. But if we change this to a 2 and a 2, what's going to happen? Now the dot product changes, and now we get 8, 2, 4, 4. So remember your matrix multiplication from your lessons with Jiaoshu. This is just changing the matrix multiplication a little bit. Now we're going to do np.arrange. np.arrange creates an array starting with this first number and ending with the number before the second number. So range, remember in Python, starts with the first number you give it and ends right below the second number. So now we're going to do np.arrange. This is going to do by 2s, so it's going to be 3 and 5. Why not 3 and 7? Because it ends before 7. But if we added it, change this to 8, it would end at 7. np.ones, this would create a matrix of 5 ones, or really a vector of 5 ones. So we have 5 ones, np.0, 5 zeros. This will create a matrix of 5 by 5 ones. So here we go, 5 columns, 5 rows, 5 ones. This will do the same with zeros. What happens, you can pause for a moment at home, think about this. What happens if we take the dot product of this and this? We get back the zeros matrix. Now we do the identity. So this times anything itself, and then we can do a matrix of different shapes. So now it's no longer just 2-dimensional. Now you can have 3-dimensional up to nth dimensional. Same thing with zeros. And then now we can add 5 anywhere so that you can have the matrix populated by different values, one value for every place. And then let's say we want to make one of these entries a 7. So if we do x equal x of 1, 1 equals 7. Taking a moment there. X, and then there we have it. We have 1 on 1. Remember, matrix are indexed. This one up here is the column, or so is the rows, and this one is the column. So first rows, second column. So now we're taking create a lint space. So this is going to have 2 and 3, but between 2 and 3, it's going to create 5 numbers, and it's going to return an NP array. So right there, 2, 2.5, 2.25, 2.5, up to 3. And now it's going to do the same, but it's not going to include 2 and 3. So, or it's not going to include 3 rather, because we did endpoint equals false. 2, 2.2, 2.4, 2.6, 2.8. And now we get dimensions. Remember, dimensions are the number of rows and columns. You have to match dimensions to multiply, which is really important for linear algebra. Is very important for artificial intelligence and very important for deep learning. So let's get the shape. We have the shape there. Basic indexing and slicing. Get the 0th element of B. First element in the row, first element in the column. And then here we get the first column. Here we get the first 2 second column. Remember, it ends here, so it just includes the first column and then the 0th row. So here, 1 and 2, which is because it's the, so it's not the first, yeah, so it's the first first column, and then here is the first row, second column. Here we take the matrix of A transpose. So remember, when we transpose a matrix, we flip it. Nothing too exciting there. We could also do np.transpose of A, and this is another way to flip it. Let's do a slightly more exciting one. So we have V, and so if we do V, we get an array, but if we do transpose, we get kind of the same array, but now it's flipped, so that's columns instead of rows. We do simple elementalized multiple operations. We can add together A and B, and if we do that transpose, we get something that's an operation that's a little bit more interesting. So A minus B, so now we're subtracting two numbers, or two matrices from each other, so each element of the matrix is subtracted from each element of the other matrix. We can do this with any matrix. Recall that these do not have to be the same size, but they have to have one same size. So if you had two matrices that are completely different sizes, like here, operations cannot be broadcast together with shapes 2, 2, and 4, comma, because you need at least one similar size when adding together, and you need also at least one similar size when multiplying together. So matrix multiply A and C, and then let's see what happens when we do matrix multiply C and A. That works. Multiply with a larger array, and then it won't work though if we do an array that's not the same size in the relevant dimension. So let's just do add a 5 everywhere here. np.matmul d comma np.ones. Yeah, and so the second matrix has to have the number of rows match the number of columns in the first matrix. Well, star provides the element product, at provides the matrix product. So this is the element product of A and B, meaning that you're multiplying the first number is the first number, second number is the first, second number, third times the third, and matrix multiplication. You can do type conversion, so you're converting a list to an array, and then you can convert that to an int, so that int, just like in regular Python, it takes 2.5, rounds it down. If you want to get the rank of a matrix, you can just do np.lineage.matrix_rank of B. Recall the rank of a matrix is the number of pivots. Here, the rank of the matrix is just 1 because there's only one row, and if we made it 4 by 4, it would now still be 1 because the rows are linearly dependent. To the rank of zeros, it's 0 because rank of a matrix of zeros has no linearly dependent rows because there's no span. Matrix conversion, we invert a matrix. Invert another matrix, and we take the determinant. Solve a linear system, so we have coefficient matrix, we have an output matrix, and then we do the solve, and then we get the solution matrix right here. So we can also take the eigenvectors and eigenvalue using np.lineage.eig. So here are the eigenvalues, here are the eigenvectors. Let's do that for A as well. Raise a matrix to a power. So just multiply by itself several times. Let's see what happens when we raise a to a power. We'll get something more exciting. So it's just multiplying by itself over and over again. Multiplying by the 0 power takes to the identity matrix. Here's an array with some here's an array with some imaginary numbers, and then we can do Cholesky decomposition. So when we do Cholesky decomposition, we go to L, and then we get back to the same when we multiply L by L dot transpose. So recall Lattice decomposition is when we take in matrix where L times L transpose is equal to the original matrix. Create a random matrix. So this is a bunch of random numbers with the matrix form we have. You can do the same thing again. To get a uniform random matrix drawn from a uniform from 0 and 1. So this draws from a normal. This draws from a uniform. This draws a normal random variable with a set mean and variance. Variance sigma, mean mu. And then if we do S, notice there's 1,000 variables, so it might take a moment, but there we go. And then mu dot np dot mu to s. So it's not perfectly the same, but it's only less than 1 standard deviation, 1/5 of 1 standard deviation away. And then we do sigma minus np dot standard deviation, so how close standard deviation is. Standard deviation is 0.00095. And standard deviation here is 0.1. So standard deviation is lower. Why is the sample standard deviation lower? Because standard errors decrease as the actually that sorry. Let me go back. That is the variance. np dot square root. So let's see what happens when you take. Yeah, so there's a pretty big difference between the standard deviation and the found standard deviation and the applied standard deviation. There's a very small difference between. That's right. Sigma is the standard deviation. There's a very small difference between the standard deviation and the found standard deviation. Now we plot S. So notice we get something that very closely approximates a normal distribution. Maybe there should be a little bit more of a peak here. We've also, luckily enough, plotted this normal distribution on top of it. So now we set a seed. This means that when we take the random numbers, it's going to give us the same random numbers every time we run this code. Not every single time, but if we do this, it will give us a different one every time. But if we set the seed again, it will go back to the beginning. Do random choice, and what this means is it's choosing from a list. Here, it's choosing 3 numbers between 1 and 5. Here, it's choosing 3 numbers between 1 and 5, where 3 is the most likely. Between 0 and 5, rather. 0 and 4. And then we do random choice from 5. If you count 3, we replace equals false. So you can't get the same number of numbers. You can't get the same number over and over again. And then we can do shuffle here. Range shuffle. So what shuffle does is it should randomly switch off the numbers in the matrix, but it's not. It doesn't seem to be doing that. So it's, all right then. But yeah, it should be shuffling. And then we take the log of the random matrix. So notice some of these are nons. If you recall, the logarithmic operation does not apply to negative numbers or zeros. So that's why those go to NaN. We take the exponential. That applies to everything. So you have everything in the matrix raised to an exponential, taking the square root. Notice you can't take the square root of a negative number, and we generate a normal random variable. Take the sine, cosine. We sum along the first axis, which means that we sum all of the numbers by column. We sum along the other axis, which means we sum by rows. We take the mean. We take the mean with respect to the 0th axis, which means we take the mean by row. Now we do the same by column. Take the median. NP to array does not have attribute median. PD.median. We'll leave it as is now. NP, random matrix standard deviation, standard deviation, variance. Let's just, I think we can do median. It's a good example of how to debug. You just search for what you want to do. Yeah, I should have just done np.median. So np.median. And there we go of the median, very close to 0, as it should be, because it is a standard normal random variable. Let's look at the graph, and you can kind of see that makes sense. It's a little bit less. Take the minimum, take the max. Should be very similar because this is normal random variable. It's not standard normal. It is a standard normal random variable, I guess. I think. No, it's not. Oh yeah, it is, because we did no, it's not, because we did 0.1, not 1. So we do QR decomposition of the random matrix. So we decompose into a Q and R that multiply together. One is a upper triangular matrix. And so np.close, it checks whether or not they're the same, and it's true. And now we do norms. Norms are very important in linear algebra. Norms are very important in machine learning. Basically, what a norm is it's a way to measure something. So remember that a norm has the properties that 0 when each value in the distance between, it's 0 when you hand in two things that are the same, and it's non-decreasing in terms of the vectors, and it is never negative. So it's just a way to measure how large things are. So we take this np.range minus 4, so we have this number, and we take b equals a.reshape, and then we take the norm of a. So this is the norm, which is the Euclidean norm. We can also do the -2 norm. We can do the 1 norm. We can do the infinity norm. Recall that the infinity norm, the 2 norm is basically a Euclidean distance, and the infinity norm is raising everything to the infinite power and taking the infinite root. Here we do singular value decomposition, where we take the SVD composition of U SVH, random matrix, stack vectors, HStack. We concatenate two vectors. We split two vectors. So we split a vector into multiple vectors. So we split the vector into three vectors. So we have x, and that's one vector, and then we split into three vectors. And now we can do linear regression, finally. So linear regression is something you'll be required to do in your homework. So it's x equals np.array, y equals np.array, a equals np.vstack. So let's look at what each of these objects are. So x, y, a, x, y, and then a is just a matrix with x and then ones. We add the ones so that we can have an intercept. So we run the regression. We have an array 1, 0.95, which is a intercept of 1 and a coefficient negative 0.95. We do linear least squares, and we get the same results. Little floating point division error here. And here is the fitted line, the original data. And here is the same thing. This is using our regression, and this is using built-in linear squares. So recall regression here is np.linear algebra inverse of a dot transpose at a at matrix multiplied by a dot transpose at y. So yeah, that's our little intro to Numpy. I hope you enjoyed it. I hope you're following along, and I hope you have a great day. Bye.